Okay, so my clock shows that it's 1:20 p.m. right now, so we can start. Welcome back to Introduction to DSP. Okay, so how are you guys doing? So today, let me just write my plan on the board behind me. Okay, just as a kind of an overview. Today's agenda. We will be talk about two topics, right? So the first topic, let's say today's plan. The first topic I want to cover is a version of Fourier transform that's called DTFT, which stands for discrete time Fourier transform. Fourier transform, you know how to spell transform, okay? So discrete time Fourier transform, 离散时间的discrete time an adjective 是一个形容词So you'll see that after many years I have memorized the definition, right? So you'll see that we will obtain a spectrum that's denoted such, and we'll cover the detail, but I've memorized the definition. It's going to be take us from time domain, and then e to the minus j omega n to the frequency domain with sum over all n. So that's the very definition of discrete time Fourier transform, which goes from time domain to frequency domain. So we'll introduce that, and especially I will try to motivate what's going on. Why do we need this definition? Why does it make sense? Okay. So after introducing this definition, and then we will cover quite a few properties, okay, that we all find useful in general, and in particular for your homework that we are going to discuss tomorrow. Okay, tomorrow there will be a homework discussion session, right? So we'll cover about its properties, various properties of DTFT, right? So that's the first topic. And probably toward near the end of the second hour, I plan to talk about conversion. Okay, so in the first 2 weeks of the classes, we covered conversion from continuous to discrete, right? From continuous time to discrete time. We say basically it's sampling. Yeah, that action is sampling. And we mentioned that if we sample fast enough, then we expect that we can reconstruct, right? We expect that we can reconstruct the analog signal, okay, but how? So today we will in general talk about the idea that we need to be able to go back from discrete time to continuous time, okay? Let's say we have a sequence of signal that has been sampled from some kind of analog, and then from there, how do we go back to the continuous time domain, to the analog continuous time domain? So this is a question mark. How do we reconstruct a signal so that under the criterion we sample fast enough, this reconstruction will be perfect reconstruction. In the quadratic criterion, we expect that the reconstruction should be equal to the original signal in the analog domain, in the continuous time domain, right? So those are the two topics, two lectures I want to cover today. Okay, today we have 2 hours finally, right? So let's start. Okay, so yeah, let's focus on the monitor. There's a screen right now. So again, this lecture, the pre-note, this pre-note has been uploaded to EE class. So please, if you haven't done so, please download it so you can take a look. Right. And so let's start from a recap, sort of a review that we have the continuous, we have here is a definition denoted as a script F, 草写 FR, which goes from time domain to the frequency domain. And in this case, our frequency variable this is our frequency variable in radian per second, okay? It's a continuous spectrum this is our definition, okay? The kind of definition that we have for the definition for Fourier transform. And you can apply it to go from, you can apply it for any time domain signal so that the result is a spectrum, okay, as a function of frequency. Okay? So the idea is that we check how much of a component this signal has at every frequency, okay, by doing this, by this integral. So this integral essentially is a projection that's done by taking inner product. So this is essentially an inner product. Okay? So you'll see that in later different version of Fourier transform, always the notion of inner product is right there. Okay? So I have some remark. This really is the inner product of two signals. Which two signals? It's an inner product of, we can denote xt with e to the j big omega t. So this this integral gives us the inner product between our signal of interest. This is our signal of interest, the signal that we are interested in looking at. And then we, by inner product, we project the signal from time domain to frequency domain. So that's the idea for continuous time Fourier transform. And so far, so good? Yeah? And in this lecture, as I said, we will introduce DTFT, discrete time Fourier transform, DTFT. So let's memorize it, discrete time Fourier transform. Okay. But before we even start talking about math, so at this point, I also want to mention that there is yet another version of Fourier transform that has a very similar name. Very similar name. Okay. There's yet another kind of Fourier transform that's been called DFT, where D also stands for discrete. Okay. So it could be a bit confusing, at least for me as a student. I was confused a little bit because discrete time Fourier transform, and there is a discrete Fourier transform, two different things. Okay, of course, then they're related. So we will introduce DFT later, but let me mention just for your information. DFT really has what's different between DFT and DTFT is that in DFT, the frequency domain is also discrete. Okay, we have finitely many lines, frequency lines in the frequency domain. So in DFT, really, this discrete, this adjective, 这个形容词 is describing the Fourier transform. So emphasizing that it's discrete in the frequency domain. In the frequency domain. So that's the difference. And just later you'll know that then you need to know that, okay? You will need to know that what we say FFT, the fast Fourier transform, is nothing but a fast implementation of DFT, okay? FFT is a fast implementation of DFT, which is discrete in both time and frequency, okay? So we'll cover that later in this semester. But today, our focus is the DTFT, which I wrote down on the blackboard. Okay, this is a definition. We'll reach this definition. Okay, okay. So now, next, let's start talking about the motivation behind DTFT. The motivation. So the motivation really is to have a representation for a signal after it is sampled. After it is sampled. So what is going on here is that suppose that we have a signal x of t, okay, x of t, and then we sample it, right? We apply C to D conversion so that the result is a sequence of numbers, okay? And we say that equivalently, we can think of sampling as if the signal now becomes an infinite series of impulses. After sampling, now time becomes discrete, so you can think of sampling as to transform a continuous time signal into an impulse, a train of impulses. A sequence of impulses. And we have been drawing a picture like that. So in the last lecture, we draw a picture that suppose, just to illustrate the idea, suppose that this is our signal in continuous time, Then after sampling, we change it, we convert it into a sequence of impulses, right? Into a sequence of impulses. And every impulse is represented as a delta function. Yeah, that should be clear, right? Every impulse is represented by a delta function, but their heights are modulated according to the value of xt. So that's why we have this expression right there. Okay, that's why we have this expression right here. Now, after sampling, the signal becomes the sum of a sequence of impulses which are located at the time instance of 0, 1t, 2t, and so on, right? The impulses are shifted to the right. The impulses are shifted to the right by this amount, and then their height is according to our signal of interest. Okay, this is continuous to discrete conversion. Okay, conversion. So this is our expression. So now, if we just substitute this into the definition of Fourier transform, the good old continuous time Fourier transform, right? Let's consider the Fourier transform of sampling, okay, of the result after sampling. Okay, if we do that, and last time we know that in the frequency domain, you expect that the spectrum is going to be repeated periodically. Yeah. Last time we emphasized on that aspect. 我们强调这个角度啊 we emphasize on that aspect. But this time, let's just plug it in. Okay, plug x this sampled signal. Plug it into the definition of Fourier transform. So then we go from small x to big X. Right? This is our convention. The convention of our notation. This is 就是 notation 符号的习惯啊。The convention is for the time domain for small letters, lowercase letters for time domain, uppercase, big X for frequency domain, right? So this is nothing but just a definition of Fourier transform. Nothing more, nothing less, right? So just plug it in and then now use this expression. Then just substitute substitute xs with this notation, right? This is just substitution. 代入而已啊 substitution, right? Just substitute our signal with, now of course we know that now it becomes a sequence of impulses, right? So then we just plug that in. Just substitute our signal with this summation expression, with this very expression. With this, wait, yeah. Where is my highlighter? No, yeah, I like this. Yeah, just make the substitution, and then what's next? Okay, I wrote off something's wrong. Yeah, this I realized there's an error. Okay, let me just. Does anybody spot an error? This is wrong. This should be minus infinity to infinity. Right. Sorry for the mistake, but I'm glad I found it. Yeah. So anyway, so after substitution and correctly setting the summation range, the range of not summation, integration, the range, the interval of integration is from minus infinity to infinity in time. Okay, in time. This is the integral with respect to time. Yeah. What's next? What's next? So by just taking a look at this expression, so usually if you want to use the integral and summation, the next step is what? You try to change the order, right? Try to change the order of summation and integral. I recommend doing that. Usually we don't worry too much in the electrical engineering department. Okay, so in math department they worry about this a lot. Okay? Whenever you change the order of integral and summation,他会揍你拔你的头 But they are not happy about changing the order arbitrarily. But here we typically don't worry about it. Okay, so let's try. What if we change the order of summation and integral? Okay. So after changing the order, then what we can do is that for anything that does not explicitly depend on t, we can pull it to the outside of integral. Yeah, okay? Linearity, right? So this is simply linearity of integration. 积分是具有线性的 linearity. So we can pull anything that doesn't depend on small t to the outside of the integral, move it outside, okay? Move it outside. So after moving it outside, then what remains in the integral becomes pretty trivial. Why? This is trivial because we are integrating in time for sure, but the only time where this expression is not zero is right at t equals to small n, big, n times sampling period. So the only time this thing is equal only at t equals to n times sampling period. Otherwise, it's equal elsewhere. It's zero elsewhere. So this is the basic property of delta function, right? So then we all know that for delta function, if we take the integral, then the result is equal to evaluating this coefficient right at that time. Is that too fast? No. So this is the result, okay? This is the result of e to the minus j omega t evaluated at t equals to n times sampling period. Why? Because this delta function is non-zero only at that time. It's non-zero only at this time, okay? Okay, so that's just a few steps. 1, 2, 3, 4. Okay, 4 steps. So now we have an expression for the spectrum. But now it becomes a summation. The integral is gone. The integral disappears, right? The integral is gone, has been dealt with. Okay, we no longer see the integral. So now we have an expression of the spectrum in terms of summation. Is that clear? Okay. After sampling, now the expression we have successfully reached a definition, an expression for the spectrum for that sample signal, okay, for that sequence of delta impulses. Its Fourier transform can be expressed in terms of a summation. That's something new. Okay, that could be something new, right? For sampled signal. Okay, it's Fourier transform. And we are not even using a new definition of Fourier transform. This is good old definition of Fourier transform. But now we found that, hey, the spectrum can be expressed as a summation. Summation for what? Summation index is n. N is for all n, okay, for all integers. Summation index n, and here, what's that? That's that, right? X evaluated at n times the sampling period. That's the one number in our sequence. That's one sample. Okay, so this is basically one sample, and then so now all we need is to now focus on this part. N is right there, and T is right there. But here is the frequency in radian per second. That's the angular frequency in radian per second, 2 pi times hertz. Okay, 2 pi times frequency. But now, wait, how about we define? So here is a change of variable. Now, the next thing we do is to introduce a change of variable. So we are going to select a new frequency variable, call it small omega. Okay, and this small omega is going to be defined as sampling period times our good old big omega. Big omega again is radian per second. Okay, radian per second. So hopefully by introducing this change of variable, we can simplify our expression just a tiny little bit. And it is true. Okay, this is about simplifying our notation. Okay, so by introducing this new frequency variable, which is denoted as small omega, then now we go back to this expression. When we go back to this expression, after introducing this new frequency variable, now we have a new definition of spectrum. Okay, now we have a new definition of Fourier transform that tells us that for a sequence of number, denoted as x of n, okay? For this sequence of number, which represents a sequence of delta impulses, okay? So for any result of sampling, it now seems to us that we can define such. The sequence of number representing a discrete time signal, okay, with constant sampling rate. A discrete time signal with constant sampling rate. Now, its Fourier transform can be expressed as a summation, as we have derived it. As a summation of xn times e to the minus j. Now, be careful. Minus j, and take a look. Now, this big omega times sampling period is our new frequency variable, right? We define a new frequency variable, which equals to big omega times sampling period, right? So now, just take a mental picture of this. We are going to write it down, just right here. We are going to write that down, copy it. E to the minus j and small omega n. So now it becomes a definition, a good definition of Fourier transform for any sequence that's a result of sampling, that resulted from sampling. Okay? For any signal that resulted from sampling with a sampling period big T, then we can define its spectrum with this expression, okay? And we just we recommend calling it DTFT. This is our definition of DTFT, which really has a motivation from good old Fourier transform, but it can be applied for discrete time signals. So that's a motivation, okay? Simply we introduce the key point to keep in mind is that we introduce a new frequency variable. Okay? This is important. It's important to always keep in mind that there is a new definition of frequency variable. But then we can have a few discussions. Okay? First discussion: what is the unit of this new frequency variable? What is the unit of small omega? What if the unit for small omega, when we say small omega is defined as this, right? Then can anybody figure out? Then we need to figure out what's the unit. Okay, what's the unit of small omega? Okay, so to answer that, the unit, right? The unit should be time multiplied by radian per second, right? So the unit, my answer is, the unit, okay, is time, which is, let's say, second, multiplied by radian per second, okay? You can plug in number, For example, the sampling period is 25 microseconds, seriously, okay? So just, then small omega has the unit of second times radian per second. So it turns out that it has a unit of radian. Okay, small omega has a unit of radian. So later in this class, we will repeatedly talk about the unit circle. Okay, it will be clearer. But we really seriously, later we will often draw a circle and then treat omega, somehow it works. Treat this angle. Omega is an angle. Okay, omega really is an angle. Okay, later we'll see the omega is a z domain actually. In the z domain, omega is equivalent to any angle on the unit circle. Okay, but here it's correct that to realize that the unit is radian. Omega is an angle between 0 and 2 pi. Okay, an angle between 0 and 2 pi. Omega is an angle, typically you name it, it can be between minus pi to pi or from 0 to 2 pi. Okay, it repeats itself. So omega is really an angle. But really, when we talk about unit, okay, we talk about unit. I prefer to think I would suggest that first of all, let me point out that later we will just stick to this definition. We really will not go back to the good old Fourier transform anymore. Okay, hardly. We hardly will go back to the continuous Fourier transform. So in the rest of this entire semester, we will stick to this definition. Okay, and we will see that it is an adequate representation of the signal. 它是一个充足的、足够的 adequate. Okay, it's an adequate representation for our signal in discrete time. Okay, so we just stick to this. This is a very important definition. Okay, we need to fully understand it. Yeah. But then I want to point out that then when we say this small omega is from 0 to 2 pi, okay, it goes around the unit circle. Yeah. But I want to just share with you that often in my mind I would automatically translate how many hertz does omega really correspond to. Okay, let's say for example if omega is 45 度 or is 45 degrees, or pi divided by 4. Okay, in my mind I always automatically translate that into 45度的话 45 degree is what? Is 1/8 1/8, right? Like a pizza, right? You cut the pizza into 8 pieces. 45 degree is 1/8 1/8 of the sampling period. It corresponds to that actual frequency. Okay, so I just make this automatic translation between small omega and big omega. Okay, because that is what this definition is trying to tell us. Okay, so you want to be able to make the conversion between small omega and then big omega, and there's a remark. Okay, there's a remark. For example, omega of pi divided by 4 may correspond to a frequency of sampling rate divided by 8. So you want to make sure that this correspondence can happen automatically in your mind after taking DSP. Okay, when we go from hertz to small omega, what's going on? Okay, that's a conversion. Or that's the kind of exchange, currency exchange. 怎么样汇率? Or that's a currency exchange between hertz and small omega. Because small omega is an angle, it always is between 0 and 2 pi. Yeah. But actually 2 pi corresponds to sampling rate. 2 pi corresponds to sampling rate. Okay? 2 pi corresponds to sampling rate. 2 pi corresponds to sampling rate. 很重要，讲3次. Right. All right, so that's a way to really look at this definition. Okay, practically, that's what's going on. 2 pi corresponds to sampling rate. Right. Yeah. Okay. So that's a bit of a kind of about the notation and convention. It takes a while to become used to it. Okay. 要一会儿才会习惯了啊，坦白讲啊。It takes a while to become used to it, but you will get to that point. Okay. No worry. It's very simple. Okay. It's very easy. Yeah, I can assure you. But next question I want to throw to you. So it's an interesting one. Okay. So now when we examine this new definition of what we call DTFT, right? The idea is go from time to frequency, right? So the result is a spectrum. We take a signal in time and convert it, and then we convert it into a spectrum in frequency, right? So the result here is a function of frequency, for sure, right? But why do we have this notation? This is weird. This could be weird, right? If it's a function of frequency, why don't we just write it the easy way, a function of frequency, right? There should be nothing wrong about this. Because the result is a spectrum. A spectrum is a function a frequency, why don't we just write it this way? Why do we write it in this strange way? And I think that's a good question. Okay, yeah. If you ever have this doubt, yeah, I agree with you. This is again, there is a reason for this. Okay, there is a reason for this. The reason will be clearer when we introduce Z transform. Okay, because the answer, this is to kind of have a unified notation between DTFT and Z transform. Okay, so the reason that recall, for those of you that have taken signal in the system, recall we have a Z transform defined as summation n xn what z to the minus n. Okay, that's the definition of Z transform. We'll go back to this. Okay, in chapter 5. Okay, later this month we'll officially review or introduce Z transform. But the reason why we have this notion is turns out that DTFT equals to Z transform evaluated on the unit circle. Okay, Z transform, let me just write the entire sentence, evaluated on the unit circle on Z equals to e to the j omega. That's a unit circle. E to j omega is a point on the unit circle in the complex plane, on the complex plane. Okay? So the reason why we have this notation is to agree with the notation of Z transform, which we will introduce later in this semester. Okay. So there are a few kind of potential questions, so details that maybe look suspicious. Yeah, so I want to explain to you before we dive into properties of DTFT. All right? Hey, unit is radian, okay? And omega is an angle. Now it's, or you can say it's dimensionless. It doesn't have the unit of hertz anymore, okay? So omega equals to pi divided by 4 does not mean the frequency is what? 0.57 hertz. No. Unless your sampling rate is what? I don't know. But that's not right, okay? That's not right. Because now we have a new frequency variable, which is which is an angle and its unit is radian. Okay, it's not hertz. Right? No. Okay, yeah. Okay, so let's now move on to talk about the next step is inverse transform. You can go from time to frequency, and you can go back from frequency to time. Okay, given a spectrum, can we construct a signal back in the time domain, in the discrete time domain? Okay, it turns out that inverse transform is can be expressed by this. This is the inverse transform, the inverse DTFT, the inverse of DTFT, or inverse transform, which goes from frequency to time. It goes from frequency to time. So what's happening here? Okay, we take a look. If we now invite you to take a look of this expression together. Let's take a look of this expression together. Okay. So it starts with a spectrum. Okay, and spectrum. What does a spectrum tell us? A spectrum tells us how much of our signal has at every frequency. It's a projection onto the frequency domain, right? And so now we are having a weighted, not sum, but integral. So according to this density spectrum, which is a projection, we are going to just multiply this projection value with a signal. Actually, this is a signal. E to the j omega n is a signal. Let me write it down. This thing is actually a complex exponential signal. Not system, signal. So just by considering all the frequencies. Considering all the frequencies. Oh, I make a mistake again. This is strange. Sorry, this should be from minus pi to pi. Okay, I made another mistake. In different places. Right. So if we just consider all the frequencies, what are all the frequencies? All the frequencies, that means just take an integral from minus pi to pi. Considering all the frequency and collect everything, right? This is about collecting everything. We are collecting 收集, we collect everything, all the different components. We collect all the different components and then just put it back to the frequency, to the time domain. Okay? Every wavelet, 一个小波, or every such thing is a wave component, right? This is periodic, this is a wave component. And we collect all the frequencies and weight them according to their spectrum. Okay? This is about weighting, this is about collection. Okay? Collecting all the frequency, and the result, and it's not that important, that it turns out that there's a normalization factor of 1 divided by 2 pi. It turns out that we need this. Okay? It's not that important, but it has to be there. Okay? Then with this correction, with this normalization factor, we can successfully go from frequency domain back to time domain. Okay? That's the meaning of inverse transform. And here, sometimes, especially in my domain, my field is audio processing, audio processing. Sometimes we call the action of going from frequency to time, we call it synthesis, because the result is synthesized back in the time domain. So we can listen to it seriously, okay? So we can listen to the result if it is an audio, if you are for audio. Or we can take a look at it if it's a camera or a projector, right? Okay, so this is sometimes in some certain context is called synthesis, 合成. We go from frequency domain to time domain. Okay, so the important meanings is that this is cool. Okay, we have now a definition of DTFT, which goes from time to frequency, and then it also has an inverse transform. So the important meaning is that now we have an invertible mapping. Okay, it's a 1-to-1 mapping, an invertible mapping, 一对一的对应式. Now we have what we have is an invertible mapping. An invertible correspondence between any signal. Just allow me to say any, okay? Yeah. To have a 1-to-1 correspondence for well-behaved signal. 如果它乖乖的, well-behaved signal. So we can say that this first transform is a 1-to-1 invertible mapping for well-behaved signal between time and frequency. So this is a kind of bidirectional arrow, okay? We have a bidirectional arrow pointing to the right from time to frequency, and then from frequency we can synthesize signal back in time. And you can repeat that, repeat, and they become time-frequency pair. Okay, we can pair them up for a signal and it's for a transform. Invertible mapping, okay? So don't worry about the transform cannot be inverted. No, we have an inverse transform. We have an explicit expression for 这个很明显的一个表达式. We have an explicit expression for inverse transform that goes this way, right? So the next thing here is for us to check that this is correct, that this expression is correct, mathematically rigorous, okay? Ready? Are we ready? To check that this equation is correct, okay? So how do we do this? How do we make this check, check? So to check that this is the correct relation, then we just say, all right, summation, integral from minus pi to pi. What is the spectrum? Now, how about we plug in the definition? Because here we need to plug in the spectrum, right? So the spectrum is equal to summation let me put my index m, okay? A dummy variable, and then we put xm e to the minus j omega m. So that's our definition of DTFT, right? This is definition of DTFT, which we just introduced, right? And then copy everything right there. Yeah, we are going to check on this integral to see what it gets, what it gives to us, right? What does this produce? Now again, when you see an integral and summation, what do we try? Again, same idea, good old trick, right? Whenever you see a summation and the integral, okay, we try changing the order, okay? Changing the order, so it should equal to summation n, and then we put anything that does not depend on omega, we put it to the outside of integral, right? Same idea. So what thing does not depend on omega? The only thing that doesn't depend on omega seems to be xm, right? So put it to the outside of the integral and then consider integral inside. So inside the integral, we have e to the minus j omega m minus n, right? D omega, okay? Now, so now consider this integral, okay? It turns out that this integral is 0 if m does not equal to n. Both of them are integers, okay? M and n, both of them are integers. Let's say 10 and 20, right? When m and n don't equal, when they are not equal, then this integral turns out to be 0. Why? Because exponential j, that thing is cosine plus j sine, right? It's periodic. So 正负, yeah, positive part, negative part, they cancel. Okay? So this integral is 0 whenever m is not equal to n. Okay? That's what I'm saying right here. Yeah. But how about if m equals to n? It's even easier. When m equals to n, what is this? E to the minus j something 0, right? So this is 1. So it will equal to integral, sorry for crossing the page boundary, so I'll fix that later when I go home. But yeah, so from minus I to pi, and inside is 1 d omega, right? When m equals to n, and this equals to 2 pi, when m equals to n, okay? All right, so now this integral is mostly 0 unless m equals to n. So this summation now becomes pretty trivial. Okay, it's not really a summation. E is non-zero only when m equals to n. And at which, when that happens, its value is 2 pi. Right? So what? So now we reach the conclusion that this result is equal to 2 pi times x of n. Yeah. And that concludes our derivation. Right? It actually concludes our derivation. Does everybody see that? Okay. It actually concludes our derivation. Right? Oh. 2 pi here, 2 pi there. When we divide by 2 pi, it gives us back x of n. That's what we need. Yeah. Okay, so yeah, you can easily check that this should be not so that hard to follow. Okay, so we have checked, we have examined that, hey, indeed, that expression is an inverse transform, which starts with the spectrum and it gives us back, it synthesizes our signal back in the time domain. So that's a cool definition. Okay, that's a great definition. It's correct. That expression is correct. Okay, nothing to worry so far. Right. All right. So let's can we move on? Yeah. Yeah. Okay. Yeah. Okay, so um, let's see. Let me take a look at my plan. Okay, so I will talk about this topic, but let's push it later. Okay, maybe in half an hour I'll talk about conditions for existence of spectrum. Turns out that when I say for any xn we have a spectrum, this is actually not right. So remember I said only well-behaved signal can have a spectrum. Okay? That is true. Okay? But so there are some criteria for us to check whether to have the right expectation when we have a signal. Let's say when it doesn't converge in the time domain, when it's diverging, right? Can we calculate its Fourier transform? Sometimes the Fourier transform does not exist. Okay, sometimes that sum it does not converge. Okay, so later we will talk about conditions for existence of the spectrum, but let's push it to later. Okay, let me cut it and move it to my final page, maybe somewhere here. Yeah. Okay, we'll talk about it. Okay, but don't worry about the existence for now. But I want to talk about something simpler first, easier thing first. Okay, so first we can now examine a few properties. Okay, we can now examine a few properties. Okay, a few properties of, sometimes I still just without any without confusion, okay? 如果没有造成混淆的话, so sometimes I still I use this notation, x of small omega is to denote a spectrum, right? Just to be not confused with, sometimes we use this notation, sometimes we use this notation. It's kind of sloppy, okay? But you know what I mean. So this is a spectrum. Okay, so now I want to show a few properties. The first property we need to understand, we need to look at together, is that x of omega is always periodic. Okay, x of omega is always periodic, and the period is 2 pi. The period, really no surprise, is 2 pi. When I say omega is an angle, okay. Turns out that x of omega for any spectrum, any signal, whenever its Fourier transform exists, we calculate its Fourier transform, and its Fourier transform is a function of omega, and that function is always periodic with a period of 2 pi. Okay, that is x of omega plus 2 pi is always equal to x of omega for any omega. Okay. That's the first important property. And we can easily check that. To check, let's write down our new friend. Okay, the definition of Fourier transform is summation n xn e to the minus j omega n, right? Now sum over all n. Therefore, when we evaluate the spectrum at omega plus 2 pi, what do we have? All right, that's the question. Right? That's the question. When we evaluate the spectrum at omega plus 2 pi, still we have the sum, right? And xn, just copy it. E to the minus j, now we have omega plus 2 pi n, right? And I'm again running out of my space a little bit, so I'm going to move this thing, make it smaller, and move it maybe here. Okay, okay, so let's focus on this. It should become clearer that now this is equal to summation, just copy everything, xn e to the minus j omega n e to the minus j 2 pi n. Right? And what is this? this is not just 1. N is an integer. E to the to 2 pi, n being an integer, right? So this is always 1. And what is this? This is equal to x of omega, okay? X evaluated at omega 2 plus 2 pi, it turns out it's always equal to x of omega. Any discrete time Fourier transform will be periodic, will repeat itself every 2 pi, okay? So that's a simple enough property for us to understand. Next thing, we have the shift theorem, okay? So my notation goes this way. Next property, if x of n correspond to big X of omega, time frequency pair, if they form a time frequency pair, xn in the time domain, big X in the frequency domain. Now, when we shift our signal to the right by m samples, you with me? X shifted to the right by m samples. Shifting to the right, 往右边移 by m samples. And the result, of course, is denoted as this, right? This is x shifted to the right by m samples, okay? Where m is a fixed delay, or if you will, okay, a shift, and n is our time index, okay? Yeah, n is our time index. So now when we shift our signal to the right by m samples, when we shift our signal to the right by m samples, what happens in the frequency domain? That's the question. Okay, that's a property. Okay, and turns out that I'm going to show this. Turns out that it's Fourier transform. Now, if we take the Fourier transform, the result relates to the original Fourier transform, but now with multiplying a complex phase term, minus j omega big M. Okay, yeah. The resulting Fourier transform now is the spectrum multiplied by a linear phase term. We call this a linear phase term. It's modified by as this. Okay. Okay, so this is so I'll leave the checking to you. Okay, check. Just homework. This is what exercise may involve. I don't know. Yeah, change of variable or something. Yeah, this is exercise. Okay, but I do want to talk about property. Okay. Okay. Now talk about, let's contemplate this result. Yeah, let's contemplate 凝视. Oh, I like the term. I like the verb. Contemplate on this result. Okay, I'll enlarge it. This is what we have. When we shift the signal in the time domain, we claim, I'm telling you that the spectrum has this, the resulting spectrum is the origin spectrum, but multiplied by this, okay? What does that mean? What does that mean? So there are a few observations that we can make, okay? So maybe it's about time to talk about when we have x of omega as a spectrum. Usually we can talk, we're for sure x of omega is modulo. It's an absolute value times e to the j, the the phase spectrum of x of omega. Can we agree on that? Because the spectrum, when we think about the spectrum, is really complex valued. So this I want to emphasize, bring it to your attention, okay? The Fourier transform, when we under that definition. In general, the spectrum is complex valued. At every frequency, we have the real part and imaginary part. Okay, this is serious. So So at every frequency, what's happening here is that now omega is from 0 to 2 pi because it will repeat. Okay, but now seriously, the most correct way we should talk about the real part of our spectrum versus there's an imaginary part of the spectrum. Yeah, so the spectrum really is complex values in general. Okay, and you can try to picture how to draw a spectrum. It really has the real part and the imaginary part. Okay, so instead of drawing the real part and imaginary part onto the same plot, which becomes 3D, this is too complicated. Okay, so usually we just usually we would so here usually we have the habit to separately talk about the absolute value, and we call this the magnitude spectrum. Because it encodes the amplitude of our signal at that frequency, the amplitude. Okay. So whereas the phase of omega really, if you will, is defined as arctangent, the real part, divided by the imaginary part. Okay, you can complete the expression. Okay, real x, imaginary x. No, the other way around. Sorry, imaginary divided by real. Okay, imaginary part of x divided by real part of x, and taking the arctangent. Okay, that's a phase. That's an angle. Okay, so at every frequency we have the magnitude and the phase, and that's a very important concept. The magnitude tells you the amplitude of a signal at the frequency. The phase is relative. Okay? The phase is an angle. Okay, and now the phase and both the phase and magnitude depends on omega. That's the meaning of a complex value spectrum. Okay, so this thing can be called the phase spectrum. Okay, yeah. So now, with this shift theorem, we come to realize that when we shift the signal in time, the resulting spectrum actually does not change the magnitude. Did you realize? The resulting spectrum, okay, the magnitude doesn't change.讨厌。好，请记得提醒我 ，remind me that I will talk about if xn is real. Okay, if I will talk about if xn is real. But let's what do we have? Fourier transform. Now, shift in the time domain does not change the magnitude of the spectrum. Okay, that is, know that the magnitude of Fourier transform of x of n, right, is equal to the magnitude of big omega e to the minus j omega n, and this equals to the original magnitude spectrum. Yeah. Okay, and that makes a lot of sense, right? That makes a lot of sense when we just simply shift the signal in time. Let's say you play the music today and you play the music tomorrow. Shift it by 24 hours, right? Will that change the magnitude spectrum? No. They should sound the same. All the components at every frequency should remain the same. Only difference is in the phase spectrum. Okay? We say it introduces a phase shift, okay, a linear phase shift, but the magnitude should stay the same. Okay? So this is kind of a check of when we contemplate on the result of shift theorem, that if we contemplate that when it introduces a linear phase shift, the magnitude spectrum doesn't change, and that makes a lot of sense. Okay, so let's take a 10-minute break before we talk about what if X is real. Okay, now take a break. Hello. 好吗? Yeah. Let's get back to Fourier transform. Okay. Okay. Yeah. So let's get back to Fourier transform. All right. Um, some of you, one of you just came to me and asked about the notation, right? So I don't need to apologize, but in this textbook, really big omega and small omega have very kind of precise meanings. Okay, big omega is radian per second, small omega is an angle, right? And in other domain, in this world, in many other places, small omega is radian per second. Okay, so please pay attention, right? When we follow the textbook, when you follow my lecture, please make sure that we understand the difference between small and big omega, right? Okay, so as I promised, let's move on to talk about what if x is real. Okay, in most of time, when we talk about signal that we measure in time, it's going to be real, real value, right? Stock market, stock price of TSMC tomorrow, it never will be 3 plus 4J, right? So our signals for most of the time are real. Okay, so let's be sure that when x is real, what happens in the frequency domain? We can ask this question: do we have a property? Do we have a property when we assume most of the time we have a real value signal? And yeah, there is a property. Okay? I want to move my notes, my writing around. Okay, yeah. I'll move it to here. Hopefully, I have enough space for this. Okay, yeah. So now the second property. If x of n is real, I want to say that in the rest of this class, okay, in the rest of this semester, we will always assume x is real, unless otherwise mentioned. Okay, unless yeah. All right, let's agree that if I don't mention, then x is real. Okay, don't worry about x not being real. Okay, so if x is real, then it turns out that x of minus omega is its conjugate. Right? Turns out that we have this symmetry. This is a symmetry property. Okay? And we can easily check this. Okay? We can easily check this. If x is real, then when we evaluate the spectrum at minus omega, this is what we get. Summation n, still copy the definition, okay? E to the minus j, but now evaluate at minus omega n, okay? And of course, this is equal to summation n xn e to the j omega n, right? And of course, this is equal to that, where the star sign right there denotes complex conjugate. Okay. Oh, probably haven't mentioned that. Complex conjugate. Right. Because x is real. Okay. Yeah. So that finishes our checking. That finishes our check. All right. And this is great. Okay, this is great. Further, okay. Therefore, because of this property, when x is real, what we have is that the magnitude spectrum evaluated at negative frequency is going to be the same as evaluated at the positive frequency. Okay? Of course, the phase becomes conjugated, okay? But the magnitude evaluated at the negative frequency is going to be equal to what is evaluated at the corresponding positive frequency. Okay? We have this symmetry in the magnitude domain, in the magnitude spectrum. Therefore, one more consequence that's why when we draw an illustration of any spectrum, often we draw something of a symmetric shape, you know? Yeah. That's why when we draw a spectrum, we draw this shape, okay, which look like what kind of a, yeah. That's why symmetry, okay, when we draw any spectrum in the frequency domain, in a lot of textbooks, illustrations, we have symmetry. We always draw a symmetric shape. So in our last lecture, for example, when we discussed aliasing, right? What did I draw? When I illustrated the spectrum, I drew a triangle, right? I showed a triangle, a symmetric triangle, 等腰三角形, a triangle of equal size, right? And there's a deep reason because of our kind of agreement, okay? Let's agree that whenever we talk about signal, we assume it is real, unless otherwise mentioned, unless I mention otherwise, okay? And the consequence is that magnitude spectrum is going to become symmetric around the frequency zero. If you flip it, it's the same shape. 左右倒反, when you flip it, left to right, it's going to be the same shape. Yeah. As a consequence of signals being real in time. Okay. Yeah. So now next property, when we move on, this is another symmetry. When our signal is not only real, but is also symmetric in time, what happens? When we have a real signal that's also symmetric in time. So let me emphasize now, for now, if x is real and symmetric in time, it turns out that then x or omega is real in frequency. Okay, and you can check that as an exercise. Yeah. Okay. Symmetry in one domain being real in the other domain. Okay, that's the idea. Okay, symmetry in one domain being real valued in the other domain. Okay, and you can easily check that. Okay, now we are not going to use this property today, but we will use it later. We will use it later. Seriously, I promise you. Turns out that this is an important property for filter design. Okay, keep in mind. Okay, let me add a hashtag. This turns out to be important for filter design. Yeah, this property, and we will come back to that. Okay. All right. So now we have covered what? We have covered a few properties. First of all, the spectrum is always periodic. Okay. Secondly, when we shift in time, the magnitude spectrum remains unchanged. Third, we have two symmetry properties. When we have symmetry in time domain, we have that guarantees the spectrum is real in the frequency domain. And we have also the dual situation, time and frequency. A lot of times they are dual. We have one property, then we have a corresponding property when we reverse the role of time and frequency. 如果 time 跟 frequency 的角色倒过来的话, when we reverse the roles of time and frequency, a lot of time we have similar properties. And one of the next properties, which is also dual, is convolution theorem. Convolution theorem, okay? So first of all, let's talk about this next theorem, and it is also important. It's fairly important, this convolution theorem. Okay? Move it a bit. Okay, so first of all, we need to define what is convolution in time. Okay, what is convolution in time? So convolution in time is that the way it works is that we take two signals in time. Okay, these are two signals in times, and then the convolution produces an output. Okay, convolution produces an output, and the mathematical definition is to have a summation, and then this summation goes. We name the summation index k. Okay, so we are going to, and just in the most general definition, k is again for all integer. Okay, summing over all k, and we take a x of n minus k and multiply it with h, the second signal evaluated at time k, and then sum it up. That's the definition of convolution. That's the definition of convolution. And the notation is to use this, we use this symbol in the middle, okay? We use this symbol in the middle to denote this action, okay? To denote taking this sum, right? And the result, since k is a dummy variable, right? Since k is a dummy variable, the result is a function of n. Okay, the result is a function of n. Okay, that's the definition of convolution. Turns out that under this definition, and then now when we consider taking the Fourier transform, how about we take the Fourier transform? On the left-hand side, we denote the result as a spectrum big Y corresponding to small y. Okay, its spectrum is denoted by big Y. Turns out that big Y, when we have convolution in the time domain, we have multiplication in the frequency domain. When we convolve two signals, x and h, the resulting spectrum is the product. 是一个乘积哦, is a product. It's a product of two spectrums. Okay? Multiplying in the frequency domains, frequency-wise, multiplying at every frequency. So that's a result that we are going to check quickly. Okay, that's a result we are going to check quickly. But before we check that this is an identity, okay, 我说是一个恒等式啊. Before we check the identity is always equal, the equality always holds. Before we check that, let's talk a bit about the meaning. Why is this useful property? Why is this convolution theorem a useful theorem? The reason is because we often regard a kind of linear system called LTI. Okay? LTI stands for linear. L stands for linear, and T stands for time. I stands for invariant. 不变的, invariant, time invariant dash. Linear and time invariant systems is DSP is all about designing a linear and time invariant system, almost 90%. Okay, 90%. And it turns out that linear and time invariant systems, all you need to know about it, any of such system, is its impulse response. How does the system respond to delta of n? Okay, so the same system, if we have a system,动作太慢. When you have a system, which is LTI, and we feed the Dirac delta function to it, the result is called the impulse response, h of n. Okay, and we'll discuss, we'll make sure we understand it. This is chapter 5. It turns out that any such system is completely characterized by its impulse response. Okay, all you need to know about system is its impulse response. And for any other input, let's say for any arbitrary 任意的, for any arbitrary input that's fed to the LTI system, it turns out that the output y equals to the input convolved with the impulse response. So that's why we need the convolution theorem. Okay, turns out that output is always equal to xn convolved with h of n. Okay, x of n convolved with h of n. It makes sense. Okay, it makes sense. We'll cover this. Yeah, we'll cover this. But yeah, just to prepare us for the mathematics, we now need to officially check the convolution theorem. Given this mathematical definition, is it guaranteed? Is it really true that the Fourier transform of y will equal to the product of x and h, which are the Fourier transform of small x and small h respectively, 个别的啊. If x corresponds to big X, h corresponds to big H. Now we convolve x and h in the time domain. The resulting spectrum is simply the product of two spectrums. That's the thing, the property we are going to check next. 好吗? So far so good? Okay, so it turns out that to check is not that hard. I left enough space this time, I promise. Okay, how do we check it? So now, what is y of omega? Y of omega is the Fourier transform of y of n, right? So it's the Fourier transform of y of n e minus j omega n summing over all n, right? But now, what is y of n? Y of n, y is the convolution of x with h, right? Y is convolution of x with h. So we need to plug in the definition of convolution. Okay, we need to plug in the definition of convolution, which is right there, okay, which is right here. Okay, which is right there. So let's copy it. Okay, the yn is equal to summation now over k, x of n minus k, h of k, convolution. And then we copy this, e to the minus j omega n. Okay, yeah. And now, again, old trick. We've been using this trick a lot today. When you see two summations, what do we try? Changing the order, right? Changing the order. Again, how about we change the order? Move k to the outside, and now for anything that does not depend on n, we can move it to the outside, which is h of k. This is the only thing that does not depend on n. Okay? And then call the whatever remains inside, let's write it down, x of n minus k, e to the minus j omega n. Okay, this is changing the order of summation. Okay, so far so good. Changing the order. This is a good old trick, and we have been using it. Then what's next? What's next? What's next here? Then we can apply the shift theorem all of a sudden, right? It's the most natural thing to do next. Yeah. So k, copy. And shift theorem tells us that this is taking the Fourier transform of a signal shifted to the right by k samples, k being an integer. Okay? K being an integer. So the result should be x of omega, but with a new linear phase shift term. Yeah? Okay? Yeah. And this is because of the shift theorem. Because of the shift theorem. Okay, we're applying it. And what's next? Now, x omega does not depend on k, so we can move it to the outside of summation. And what remains inside is the summation over k. But now, e to the minus j k omega. Okay, omega k, whichever one is first, that doesn't really matter. J omega k. And this is nothing but the definition of DTFT of h, right? This thing exactly equals to, so when I write 3 strokes, sometimes my equal sign looks like 3 strokes to emphasize that this really is, it's an identity, okay? It's exactly, okay? It's kind of a 修辞, it's a rhetoric. Maybe I should just refrain from using it. It's actually equal, it's just not equal, This equal to h of omega, and that finishes our checking, Y of omega, now we have come to the conclusion that y of omega equals to x of omega time multiplied by this thing, which equal to h of omega. And that finishes our checking, okay, our derivation. This is true. That convolution in time domain leads to multiplication of spectrums in the frequency domain. So later we can think of this as frequency response, This becomes a frequency response of our system. In this context, in the context of filtering, h of omega is a frequency response that multiplies to our input spectrum, so the output spectrum receives gain, for example, at different frequencies, okay? So this is really simple, and the LTI system is characterized by a frequency response, which we often design, okay? We often design this frequency response, okay? So that kind of a general context, that's why this theorem is so important. It's probably the #1 most important theorem that we'll cover, okay, in the entire semester. So I want everybody to be sure, okay? Its derivation and its meanings. How? Okay, so maybe I can pause it for 1 minute. It seems that we have enough time to cover all of my topics. Okay, so convolution in time domain, multiplication in the frequency domain. Now this is probably the last property I will cover today, okay? The last property is also a theorem. It's called Parseval's theorem. Parseval theorem. Parseval's theorem is expressed in this identity, okay? There's an equality right here, which states that when we sum up the square of our signal in time, essentially it equals to integrating our square of magnitude in the frequency. And that's a very strong condition. This is a very strong result. Summing up, of course, we need to assume that the signal is square summable, okay? Square summable. If we assume if the signal is also known as in other words, if it is square summable, if we take the absolute value of the square and sum it up, if the signal is square summable, which means that if the summation converges, okay, otherwise it makes no sense. If the summation converges, in other words, if the signal is square summable, you can sum up the square of absolute value. If this happens, then turns out that sum equals to this integral divided by there, and there is a normalization factor of 1/2 pi. And they always equal. This is a pretty strong condition, and it is called the Parseval's theorem. A very strong condition. So when the way I kind of apply or remember this property, I can invite you to look at this property this way, okay? What do we mean to sum up this square in the time domain? Summing of the square in the time domain is like calculating the energy. Energy is, for a lot of signals, force, or let's say electrical signal, okay? When we have a voltage that drops across a resistor, right? Then the power is proportional to the square, right? And when we sum up in time or integrate it in time for analog signal, then that's an energy. That's an energy consumption. The energy. So this thing on the left-hand side, a lot of time can be called energy, even though we are lacking the unit is not right. Okay, energy has to be joule, but yeah, sometimes we just borrow the term. In digital signal processing, summing of the square sometimes a lot of times is just conveniently called an energy of the signal, even though its unit is not joule. 它并不是焦耳. But anyway, we call it an energy. Okay? So this theorem tells us that the energy can be calculated in the time domain or in the frequency domain. The energy, same sum in the time. You can sum up in time, or you can calculate the same energy in the frequency domain. Whichever way is more convenient. Okay, they will equal. You can calculate in the frequency domain this way, and they will equal. They differ by a factor of 2 pi. Okay, after normalization, they are equal. And this is for any signal which is square summable. And this is I tend to think of this as a pretty strong condition, a very beautiful theorem. Okay, a strong condition. Okay, sum of in the time domain, you can just do the calculate integral of the square in the frequency domain, and they are going to be the same. Okay, they're going to be the same. So that's the meaning. And that's why sometimes this thing square the magnitude. Okay, square the magnitude in the frequency domain. That's why sometimes it's called the energy density spectrum. Or more incorrectly, it's called power or energy. Power for random signals, energy for non-random signal. Okay, but power or energy spectral density. It's a density, really. It's a density in terms of that when we take the integral, the result is the energy. Okay, so sometimes the idea of density, a magnitude square, can be thought of as a density of energy. Okay, we can talk about how many joule per hertz when we do the conversion. Okay, when the unit is made right, then we can really, this is a density. Okay, density of energy. Why? Because when you take the integral, it gives you the energy. It gives you exactly the same result of summing the signal in time. And they are equal. This is an identity. Right? Okay, so do you want to see the proof? Or do you want it to be an exercise? Dental. This is not a yes/no question. Exercise, right? Yes, exercise. No exercise. Maybe I give you some hint. Okay, give you some hint, and the rest is details will be exercise. Okay. 卖个关子啊，要埋一个梗嘛，不然 it's no fun if I tell you all I know right away, right? There are a few tricky steps. Okay, you can probably check the answer. Maybe ChatGPT can give you a proof. I don't know. Yeah, but it turns out that there is an intermediate variable we need to define, which is called autocorrelation. Okay, turns out that we can define sketch. Okay, let me say that this is a sketch of proof. Okay. Turns out that first step is to define a autocorrelation function that's denoted by yn. Yn is equal to summation x of m, and x of m shifted by n. Okay, summation index being m. Okay, this is an autocorrelation function. And if you pay attention to this definition, autocorrelation, what did you notice? it's pretty similar to convolution, right? The definition is quite similar to convolution. But the difference is that actually it turns out that yn is x of n convolved with x of minus n, if you will. I'll leave the detail for you to agree with me, okay, to come to the agreement. So therefore, we can apply convolution theorem to this guy yn over here. Now take its Fourier transform. Okay, take its Fourier transform. The resulting spectrum is gonna be x. No, we don't need absolute value. Yeah, actually, we don't need the absolute value. It's gonna be the product of the Fourier transform of x and the Fourier transform of x of minus n. Okay, yeah. But remember that we say without, unless otherwise mentioned, I assume that x is real, right? X is real. And it turns out that this equals to x times x conjugate, okay? When we reverse in time, the Fourier transform is conjugated, okay? Actually, that's a property that I haven't covered, yeah. But you know that there's similarity. This is also symmetric property, okay? When we reverse in time, that causes the spectrum to conjugate, okay? So there are these, after these few intermediate steps, then you are ready to prove, okay? I'll leave it to you for the rest is exercise, okay? Turns out that we do need these intermediate steps, yeah. But I'll leave the rest for just for fun, okay? For you to complete the proof. Yeah. But the meaning's there. It's a pretty strong condition. Parseval's theorem, okay? Parseval's theorem. Yeah. In this homework, okay, yeah. 可以吗？意犹未尽吗？ sorry, I think it's benefit for educational purpose. Okay, I'll leave it here. Okay, I'll stop here. Yeah. But I want to mention to you that in tomorrow's discussion, if you have checked look at the first homework, the first homework has 2 questions. The second question asks you to use the Parseval theorem. Okay, so just in terms of using it, it's a good exercise. You can calculate the sum of square in the frequency domain. Okay, calculate sum of square in time, not in the time domain, but in the frequency domain. Okay, that's the purpose of the second question. So take a look in your free time. Before we meet tomorrow, I will invite you, any of you who would be willing to share your calculation to the class. Okay, so that's the second question, which requires you to use the Parseval theorem. Okay, for a calculation. 好 So please remind me to talk about conditions for the existence, okay? Because I feel like it's a lot of for you to digest, a lot of math already for you to digest or review, okay? This condition for existence can wait, okay? This can wait. In the textbook, it indeed talks about a few conditions under which the Fourier transform will exist, okay? But it seems that I have like 5 more minutes, right, before class ends. Yeah. For that 5 minutes, I want to give a highlight for the next lecture, okay? Next lecture is lecture 3, okay? Allow me to give you some highlight, go through highlight. We'll repeat everything next week when we officially enter this new lecture. But this next lecture is going to be about D2C conversion. Okay? So the idea is that, for a recap, when we have a signal in time and continuous time and we sample it into a train of impulses, the result is going to be the spectrum repeating itself, right? The spectrum repeating itself. Yeah, at every 2 pi divided by t, okay? That's a sampling rate in radian and hertz. radian per second. Okay, the spectrum repeats, and it turns out that conceptually, to recover the spectrum, how do we recover the signal in time? When we have the result of sampling, when we obtain the result of sampling becoming a sequence of impulses in time, when all we have is a sequence of impulses in time, and they can even go negative for sure. Let's say we have something like that. A sequence of impulses in time. How do we reconstruct the signal? The answer is smoothing. 平滑化. The answer is smoothing, but which exact way of smoothing? That's the topic of next lecture. Okay, we're going to suggest that we want to apply an ideal low-pass filter in the frequency domain. Ideal low-pass filter in the frequency domain, okay, which cuts off at Nyquist frequency, okay, half of sampling rate. And then it turns out that that ideal low-pass filtering, if denoted by a filter, it corresponds to a sinc function in the time domain. So we will use this sinc function, which is sine pi t divided by pi t. Okay, turns out that sinc function you can draw a sketch. Okay, we will draw the sketch, and we will discuss what does it mean to perform smoothing by the sinc function. Okay, which is equivalent to ideal low-pass filtering in the frequency domain. So that's the next topic. And we will call ideally the usage of sinc function, we call this D2C. That's the ideal way of converting from discrete time back to continuous time. Okay, we'll leave it for next Wednesday, but otherwise see you tomorrow. And please take a look at the homework when you come. And tomorrow there will be 2 sessions. If you prefer to come to the English session, come here on time. But if you prefer to attend the Chinese session, then please come here around what time? 40 minutes later. Is that clear? Chinese session after English session, each will be 40 minutes. 40分钟，好吧？好，那就 Yeah, class dismissed. Thank you. 这个是非常的 specific， 就是说有一类的 filter 会满足这种功能，我们会介绍。有一类的叫做 FR filter， 它总是左右对称，蛮好玩的。它就是这个意思。之后会讲。会。对，我口头上讲，就是表示你看这个 phase 是一条直线，phase 是欧米伽 m， 斜率为 m 直线，所以就是说叫做直线。所以是他的在讲他的 phase 是，你讲他的 phase 是直线这件事情。不过我想问一下，就是明天的作业的讲解。